actually online. This takes a second usually to catch up. Let's see. Oh, I got to get chat open there. What else do I need to do? Let's check Twitch. Am I live on Twitch? twitch.tv/LGTM_ship it. And we are... I am a mature audience. Okay, I'm here. Let me see if you are here. There are other people who join. There we go. There's the announcement. Week 8. We'll go to my dashboard. Is it channel? Dashboard. There's a whole bunch of Prime Loot. I gotta get my new games. Here we go. This is compelling stuff. There is a reason. Okay, so nobody else is here. Let's check. Ooh, one new follower. That's exciting. Okay, dashboard is very exciting. Next step is to check that we are also live on YouTube. And yes, we are also live on YouTube. So here we go. Here's the week. Here is the week. Here's the plan for this week. First, move chat into a spot where it is, where I can see it better. Move that over there. There we go. Okay, chat is positioned so I should see stuff. What is it? 7:01 usually takes a couple of minutes. Okay, so what I'm not seeing is chat showing up on screen. Test. This guy is... Oh, no, there it is. That guy's working. There was also, because nobody else is here, this is a great time to go to my own live stream. There was all new pin chat. Got it. And if I say something here, test, that should also show up on stream. But does not. Give everybody else. Oh, it seems to say that some people are here. But that's okay. I'm not going to call anybody out specifically. Manage stream. Stream manager. Okay. There we go. Oh, there, Kugelman. Good. Thank you very much. Now, here we go. So, this week, for lack of any visitors, we are going to play... we're going to play some content. So, we are here in week 8. And for tonight's show, we wanted to talk about algorithm patterns. For a number of weeks in a row now, we have discussed the way that when you are doing your LeetCode problems, actually, let's take a step back. There is a compensation course in tech. So this is one of the things that I found while I was looking around to get some information for everybody. So I have to close this, go to... Okay, we're going to find out if we can figure out why chat is not... Restream chat is not showing... Chat app. No, that's not it. Chat app. This is super compelling stuff, I know. Never mind. Wait, what if I go to Stream Elements? We will see. Maybe if I go to Stream Elements and I sign in as Twitch. Right, that other person watching is probably just me. My chat widget from here we go, my chat widget. My chat widget, my overlays, chat, edit. Okay, I can't figure it out, and it isn't that big a deal because nobody talks anyways. So the first thing, and my my camera seems to have stopped. Oof, what a week. What a week for exceptional quality. There we go. 1, 2, 3. Am I back? Yes. Haha. There we are. Okay. So while I was getting ready for this week's show, I came across something on Educative. And it was not this one. It was compensation. Grokking comp negotiation in tech. So the contents of the course are not publicly available, nor is the table of contents. But the theory is that this particular course has information on how to deal with salary. And so I went out and I found a review of the course that we can look through for free. It would have been better if anybody had showed up, but that's okay. That's okay. So the course, as mentioned in the article, so you talk about what you have to do to get to the point where you're negotiating a salary package. You've got to grind through your LEET code questions. You've got to memorize your... Well, that's not true. You don't memorize system design. You just get good enough at doing system design that you can handle it. And even then, you're not guaranteed to get your compensation package that you want. So the salary range is huge. Negotiation skills to end. So here, let's jump to the important part. So the course goes through the fundamentals of negotiation and factors that contribute to leverage. Maybe if there is some interest, I will go through and find other resources that go into detail on those things. There actually are some. What was a good one that I saw? It was... I'll search for it off screen for a second. But there was one that I watched recently. Negotiating salary tech. Where is... Anyways, negotiating salary in tech. There are a dozen or so videos. I can't see the one that I initially watched earlier on, but it is... Maybe it was Pragmatic Engineer. Pragmatic Engineer. This is the guy... Okay, so we've got a few. This this guy, Pragmatic Engineer. So it's this fella. We've met Raul before, but this guy here has a number of. This was the one. This guy has a number of tips on how to negotiate your salary when the offer comes in. Maybe I plan for adding that in a future week. So back over here, how do you interact with the recruiters and so that's one of the things they say in dealing with recruiters. You shouldn't necessarily tell them how much you are making now. And it's pretty easy to just say, that's not relevant. It's not related to what we're talking about now. The question is, how much am I worth at your company or the company that I'm going to be going to? So how do you leverage multiple offers? Now this is one that's interesting. Might be worth the course on its own. Oh, Josh, you're back. Yeah, or Josh. Or Josh. Sorry, I was very excited to see you. I thought I was all alone. Yeah, I mean that's a good one as well. I guess there are multiple strategies for this, and so using current compensation to affect a negotiation, that would be probably related to whether, if they come in with an offer that's too low, yeah, that's fine. You can be late. I'm doing this either way because people do show up and watch the videos later. Rajat actually said, he sent me a message on LinkedIn and said, "Oh, I'm not going to make it tonight, but I'm going to catch up on the weekend." So we're definitely recording for at least an audience of one. As of now, an audience of two. And then how to time your interviews for the best possible outcomes, which is, I don't know, it's really hard to do a whole bunch. It's super high stress. But this course, and I believe this website has a 30-day free trial. So if you did want to get this information, you could sign up for that, run your free trial, and then take off. So that one was interesting. It's a little early for it in terms of going for it. And so the next two things, so the first one was just to see the course review, to get a sense for when you are at the stage at the end of the interview process, what are you going to do? Make sure you check out your compensation resources. So the next, we want to be aware of, we've talked for a number of weeks in a row about how the algorithms that come up in the system design interviews are a lot like piano chords, right? So you're going to see the same patterns showing up time and again. And so these two courses that we found on Educative have lists of the patterns. So here are two, and there are more patterns, but this is sort of, and so there are actually three good resources I found on the existence of the patterns altogether. And then there are some videos down here of people who are describing the patterns. And so there are two pieces to this. I didn't buy a membership on Educative yet, but I went through the top level of this, and this is worth watching.
Trying to go through and grasp hundreds of practice coding problems before an interview can feel overwhelming. It's time to stop memorizing solutions and start seeing the patterns. Take the next step in your career. Get started today.
Ta-da! Super worth watching. Gives you the high-level overview. Was the sound okay on that, Josh? You can hear that fine? Perfect. Okay. So I'll start by collapsing all of this. The course overview. So this is for people who are already aware of the solving of the solving of the things, and you can kind of do a handful of the leak code questions. But this particular course goes through 16 pattern archetypes, and that one thing they say is all of the easy problems tend to fit like one pattern. Oh, Pebs, hooray! That's okay. You can watch the playback, or you can actually, one of the things that I do when I'm late for live stream stuff is I jump back, I jump my timer back and I watch at 2 times speed. So like I catch up to real time. But just to go over quickly what you might have missed so far. The first thing we talked about, the fact that this website Educative has a course on negotiating your salary. And then so we looked up a review of the course where they talk about sort of the themes that are covered in the course. So how to what factors come into play when you're negotiating your offer. How do you keep from telling the recruiter how much you're currently making? How do you leverage multiple offers? This one was interesting. How do you hike your current composition without changing jobs? And stuff like that. And then there's also a ton of YouTube videos that I think what I will do here. So let's load up Educative as well. Educative and grokking comp negotiation. So this site, as I was saying to Josh, this site has, I believe it has a 30-day free trial if you want to sign up for it. So you could probably just like power through this one, or buy it, whatever. It's not that expensive. But also there's a ton of these on YouTube. So it's like, there's this, that, or the other way. And now you're basically all caught up because we're talking about the fact that this particular course has 16 broad patterns of the things that you're going to see. And like we were saying, of the patterns that show up in the easy problems, you're going to find maybe that covers just breadth first search, or maybe it's just a DFS, or maybe it's just a divide and conquer, or maybe it's just a recursion, or just the sliding window. And then when you get to medium, maybe it's 2 of them, and when you get to hard, maybe it's 3 of them. But they're all built upon these building blocks in theory. And so I did want to point out this resource, again, paid course, but if you look at so does this one have a video associated with it? No, it doesn't. And that is why. So you can read these ones on your own. But what I did for this week was, if I'll hit the back arrow here, because remember on the repo you have all the links that I use. So, but if I go through and I collapse all of these, you actually have the titles of the types of patterns that show up. 2 heaps, subsets, modified binary search, top K elements, K-way merge, all of this stuff. So there's course number 1 has the list of the patterns. Here's a second course with more patterns, Fibonacci, palindromes, and longest common substring. All of these are just the archetypes of the things that show up. Here was Sean Prashad, who has his own document detailing the patterns that show up. And I think this was interesting. So, and he recommends LeetCode discussions, but this was interesting as sort of trying to come up with a shorthand for translating the problem statement. And this is probably what the competitive programmers do when they sit down and they see, the input array is sorted. So it's either a binary search or a 2-pointers algorithm. If they're asked for all permutations and subsets, then it's probably backtracking. And, so I think this is sort of like a really nice shorthand. So, I have a linked list. I probably need 2-pointers. I have, or I'm not allowed to do recursion, so I might need a stack. And so all of these are really cool. Obviously, they're not going to be 100% correct. Actually, I didn't see this Medium article before. But yeah, so they're not going to be 100%, but they are going to help you fine-tune your algorithm programming practice, where maybe on your sort of loop where you're doing your practice, you can. So I'm going to open Blind 75. Blind 75 is important, but this is the cool thing. Next cool link here. So Sean Prashad has created a list where each LeetCode question has, so we could do if I'm looking for a dynamic programming question, you can pull the drop down, you can work your way through these. He's also been super cheeky, and he's pulled out the he's pulled out the companies that they're asked at. Here we go. So I think this is a really, really nice interval. Resource. It's a really nice resource. So here's, if you want a 2-pointers question. So this should help. And what you can do in using this is you can actually go ahead and make sure, what's the B? What is B? Bloomberg? Huh. Anyways. Bloomberg. Anyways. This is really nice. So what you can do is work your way down the list to make sure you've answered at least one of each of the major patterns. Here's that same list of tips. Sort input for O of n log n time and O of... Anyway, so that's sort of the decision tree on how following sources were used in aggregating the list. So that's really cool. So this is a really good resource, I think. I'm actually going to add 14 patterns. Oof, that's a really good resource that I hadn't looked at before. If you give me a moment, I will also explain what the Blind 75 is. Code patterns. So this is 14 patterns. So we want to save that. And so blind 75 is a pretty well-known set of questions for sort of the most likely questions that you could be asked in a coding interview, as well as the ones that are most likely to cover the most common types of patterns that you're going to run into. And so it's a handful of questions for each major type. And so if you do these 75 questions specifically and get particularly good at them and get comfortable and confident with them, that should, in theory, Leet Code Premium. What's that? Can I still do it? Oh, the worst. Anyways, so that's a the blind 75 is a pretty good list. Top 100 Leet codes. Let's also put this one into the weekly links so that you have it. But I assume that Sean Prashad, his list is just the blind 75, but tagged with the type of question that it is. So here we go. So now that you are aware that the patterns exist, our next thing to do is start watching some of the... So the 2 pointers. Is this the one that I thought was good? This one's good. I like... Who does he's called Back-to-Back SWE. He is particularly good. Oh, I have to click like on his stuff. He has a great amount of content, so we'll just sort of get to know who we're talking to or listening to right now. So he's been doing these for 4 years. Is he still... Well, he did 2 and then he took a break. But anyways, still counts as 4 years. He's still producing them, not quite as frequently as he was, but I guess he was probably doing the same thing we were at the time, where he's how I got an internship at Twitter. So starting a code interview class. Anyways, we're going to watch his. He does the minimum window substring, and this is the 2 pointers technique.
Okay, so today what we're going to cover is a fairly challenging question, which is called minimum window substring. So what am I given? I'm given 2 strings. I'm given a search string or a string S, whatever you want to call it. This is the string that I'm going to need to search in. And I'm given a character string. A string consisting of a certain amount of characters, right? But this is all I care about. Do you see these counts right here? The string has 1 A, it has 1 B, and 1 C. And my job is to find the smallest window in the search string that has at least all of these characters in their respective amounts. So what the answer is, you see, is this substring right here. The substring that says B, A, and C. Do you see how it satisfies 1A? It satisfies 1B. It satisfies at least 1C. It could also be this. Do you see how I added a C at the end? But the problem is that, yes, we have 2 C's, and yes, it still satisfies, but it's not the smallest window that satisfies. That window that you see satisfies, but this window also satisfies, and it's smaller. So what we're looking for is the smallest window that satisfies this character chart mapping, however you want to call it. So first, let's look at the brute force approach, which is a sort of complete search to this, which is probably the first thing you would think of, and I'm going to decompose it and walk you through exactly what it would look like. Okay, so what I wrote for you here is if you did a decomposition of every single possible window, what would that look like? So this is a form of a complete search on the whole search space, which is every single window. And this is a valid way to do it. It's a very inefficient and very bad way. You would never settle on this solution, but this is something you could jump to immediately. If I want to find the smallest satisfiable window, try all the windows and take only the ones that satisfy and find the smallest of them. So here we have the decompositions. If my left equals 0, I have 4 windows that can be like that. If my left equals 1, I'm going to have 3 possible windows. If my left equals 2, 2 possible windows. And if my left equals index 3, that's the 1 possible window. So let's look at each of these windows. These are all the windows we wanted. We would just do some sort of double for loop. The code is in the description for this approach and the optimal approach. Code in the description. And well, you can see here is each of these windows we would have to check. Is it satisfying the constraints? So what is our constraints? That's our constraint. The character t, 1 occurrence. In my window, all I want to do is ensure, is there 1 or greater occurrences of t? Then that window satisfies. So we see here, first one, does that satisfy? No, it doesn't. Second one, does it satisfy? It doesn't. And then the third one, does it satisfy? It does not. And then the fourth one, does it satisfy? And we see that it does have the character we want. Yes, it does satisfy. And now let's remember the best we've done. The best we've done is 4, length 4. Okay, so we kept note of the best. So let's keep going. Does this satisfy? No. Does that satisfy? No. Does this one satisfy? Yes. What's the length of this? 3. Does it beat the best we've done? Yes, it does. Update our best. Okay, and we continue. Now our left, we plant it at 2, and we explore all the right windows. So now, A, does that satisfy? No. AT, does that satisfy? Yes, it does. Did it beat our best? Yes, a length of 2. So it becomes 2. Okay, and then we have just the left of 3, and then just this string. So does this satisfy? Yes, it does. Does it beat our best? Yes. And in reality, the way the code does it in the description and the way you'd actually do it, you'd keep the left and right boundaries of where you found the best. So you could chop a substring and return it to your caller. So that's just a detail, but this is the brute force approach, right? We go through all the windows, but in order to see the problem, what we need to do is do an analysis on this approach. So let's analyze why this is a less optimal solution and see how that leads us into the way of thinking that brings us to the final optimal solution. Okay, so to see how bad the solution is and see where the duplicate work is, remember, when we're optimizing an algorithm, we think of the bottlenecks, we think of unnecessary work and duplicate work. This is not my own thing. This is from Cracking the Coding interview. So why don't we find where we're duplicating work? And if we can find that, maybe we can use some auxiliary space to improve the time. You know what I mean? So if our time is high, maybe we could lower the time by increasing space, keeping auxiliary data that lets us have more information during our search so we don't go back and investigate things we've already touched. So what we're going to do is we place our left on the first window, and we're also going to place the right on this first indice. And I want you to notice how many times has each of these indices been touched. So what we're going to do is just loosely look at how many times do we conduct a window search at any given right boundary or any given right planting. So right now we're going to check the window from left to right, which is this window. So that's one window search conducted at this boundary. And then we're going to advance again, and then we're going to do another window search. And then this boundary has been touched again, and we'll increment this number right here. And then now our right pointer sits there. We're still exploring with the left pointer at index 0. So this window right here entails another search, and we're going to say that we've done another search up to ending at this index another time, so we increment that. And we'll do the same thing right here for the t. So now the right pointer has exhausted itself, and we need to increment the left pointer and reset the right. Okay, so now what we're going to do is we're going to do another window search with our right ending right there. So let's increment how many searches ending at this index have happened. So we'll increment that 1 to a 2. And then let's increment this because we do another window search, increment that, and then we also increment right there. The right has exhausted itself, we move the left forward. We do another window search ending at this right boundary. So we increment that to 3. And then another search, increment that to 3. And then what we do is we do another search. So increment that to 4. And then we do another search at this right boundary and increment that to 4. So what do you see here? What you should notice is how much we're duplicating work. How many times we're reperforming searches with our right bound ending at these indices. At this indice, when the right bound ended there, we did 1 search. We did 2 searches total with the right indice ending there. We did 3 searches, 4 searches. So that's a problem. Why are we repeating, looking at the same elements, these same characters, when we don't have to do that? If we actually looked at an in-depth analysis of this, what we could do is we could provide a lower bound for how much work we're actually doing. So this is how we could lower bound the least work we're going to do. Okay, so we're going to do a lower bound, which that's the symbol for lower bounding, big omega. It's the same thing as big O, except big O does an overbound, an upper bound, and big omega does a tight lower bounding. I don't know how tight of a bound this will be, but let's continue with it anyway. So imagine we want to lower bound this. So how many left points can I choose? Well, I can choose n left points if n is the length of the search string. So let's just say I can choose n ending points. Okay, we have n points where I can put an L like this, like that, like that, like that, and like this. So as you can see, if the length of this is n, so let's write that, we can do that n times. We can choose n left points. So if I plant myself at a left point, how many right points can I explore? At the first iteration, how many right bounds can I explore? Well, I can explore n right bounds. So let me show you that, like that right there, this, and that. So that was 4 right bounds we could do. So why don't we plant the left at the first indice, the next one? How many right boundaries can I plant? 1, 2, 3. But 3 is a fraction of this. But what we're going to do is we're still going to be doing an upper bound of n work. We're still going to be upper bounded by the length of this string in terms of right points I can choose. So let's express that right here as an upper bound of the right points we can choose. So we're upper bounded by n. And I honestly don't know how formal of writing this is. I don't even know if you can actually do that, but it makes logical sense. We can choose n left bounds, and for each of the n left bounds, how many right bounds can we choose? We're upper bounded by the length of the array. So that's an upper bound of n. And when we have this upper bound of n, in the worst case, we will have n right boundaries we can choose when L is right sitting right there. So does this make sense? N left points we can choose, and an upper bounding at each of those left points of n right points we could choose. And again, it'll be a fractional component. If L is over here, I'll have a fraction of n that I can do for my right boundaries. So what does this become? What does this lower bound us to? We know the least work I'm doing here. I'm not even worried about finding whether that window satisfies the string. I'm not even worried about seeing whether this matches against the string. That would take linear work, and if you check the code in the description, it does take linear work with respect to each string. But what you see is that the least work I can do here is n squared in work. So if you're in an interview, it's a good idea to analyze this. Tell your interviewer, well, I don't know how to optimize this right now, but let me tell you the least work this will ever do. Let me tell you the upper bound of work. It would be fairly easy to give the upper bound, but I think it's more exemplary of seeing the lower bound so that we know that maybe this could be done in linear time, right? So this is the least work we would ever do. This is a loose lower bound on this. So what we can do now is we can see how do I improve the way that I'm doing this. So it takes a little case analysis to actually see it, and that's why this problem is considered hard, because it's not the most intuitive thing, but when you see it, it makes sense. So what we need to do is we need to take an intellectual leap. And what we need to do is let's plant a left and right pointer right at the beginning of the array. We've been using pointers the whole time. That came intuitive to us. We already know how to use 2 pointers. But what we're going to see is 2 pointers can actually bring us to a linear time solution with respect to both strings. So what we're going to do first is we're going to put a left and right pointer here. So what I really want to show you is...
Here we go. Were we okay with that first half? I think it got a little thick in the... this part here in the sort of 8 to 10 minutes. But what he's saying is, you know, you've got your brute force solution, and clearly there's clearly it's heavy lifting. And now, I don't know, this explanation where they do the easier way is really cool. So
how can we get to this understanding without having seen it before? Because what I'm about to show you is it seems obvious when we see it, but in a high pressure situation, you probably would not come up with it. But how can you think about it in a natural way, right? So we had our pointers before. We've been doing that. And what we want to do is find a window that satisfies this guy right here. So what I'm going to do is I'm going to try to expand my window. What the heck? Why not? Why not try to expand this as far as possible until I satisfy these requirements? So why don't I move this forward? And again, this is in the description. The code is in the description, commented fully, so that you can walk through this, walk through that. But either way, let's walk through this. So does this window right now satisfy? Again, we're using pointers just like before. It does not. So what can I do? Well, I can add a character. How do I add a character? Do I move my left backwards? Well, I can't go backwards. Well, why not move the right forward? So let's try that. Let's move the right pointer forward and add on this character. So what I just did is I added a character on. So, okay, I have 2 choices here. I can keep moving my right pointer forward, or I can move my left pointer forward. But would it make sense to move my left pointer forward? This window does not satisfy. So if I moved my left pointer forward, it would make it even worse. It would not help me satisfy, right? So what that tells us is I need to keep searching. My left is fine. My left is just sitting there. I need to expand my right pointer until I satisfy. And then I can worry. And then I can worry about minimizing. And then I can worry about that. But first, all I care about is satisfying my constraints, my requirements. So let's satisfy the requirements. Let's move right forward again. Does that satisfy? We see that it doesn't. So we're going to continue on moving right forward. Now, does this satisfy? And we see it has an S, it has the Z that we want. So this window does satisfy. So what do we take note of? We take note of the indices. So we would take note of 0, and we would take note of 3. 0, 1, 2, 3. But I'll just write the string. Okay, so this window satisfies. But my problem does not ask for the window substring. It asks for the minimum window substring. So my window satisfies, right? And if I keep expanding it, it will keep satisfying. Because if I keep adding characters, I already know what I already have is satisfactory. It satisfies. If I keep adding characters, I'm just getting longer. I'm getting farther away from the answer. So what I should do now is now our branching goes back to the left pointer. So, okay, I know I can move the right or left, but it would not benefit me to move the right now, if that makes sense. Before, the left would not benefit us. Now the right has no benefit to it because we have the window we want. So what we do is we will move the left pointer inward, and we'll see, does the window still satisfy? If it still satisfies, then that's great. We beat this string, and that's our new answer. So that's kind of how this is going to work. So at each point, we're considering, what is the most beneficial choice for me? Should I move the left or the right? At this point, we should move the left. So let's move the left one inward. Does this window satisfy? Z and an S. Z and an S, it satisfies. So what we do is we can shorten this. That is our new answer. So what I'm going to do is I'm going to try to move inward again. Does this window satisfy? No, it doesn't. We're missing a Z. So what we need to do is we need to make a choice. Do I move my left inward or do I move my right outward? left inward will not benefit us. We're right back to square one because this window does not have what I want. If I move left in, I'll continue to not have what I want. So what we need to do is we need to move the right forward and put us into the possibility of satisfying, move ourselves forward in progress, right? So let's move the right forward. We see the window is still missing a Z, move right again. We're still missing a Z, move right again. And now this window satisfies. But it's longer than the best window we've had. I don't really care about this window. So now that we've satisfied, let's try shortening it. And let's move the left pointer because this window satisfies. We want to shorten it. So move the left inward. This window is still satisfiable, but it does not beat what we already have. So what we do is we are going to move left in again. Okay, and now we see that this window is missing an S. So we need to expand again. So expand the right pointer. Okay, the window is still missing an S, so expand the right pointer. And now the window has everything we want. This is satisfying. So right there, it's longer than what our best has been. So we don't want to take this. But what we do want to do is try to shorten this and keep it satisfying. So let's shorten it by moving L in. The window still has all that we want. And now we have this, but it doesn't beat our string. And now let's move L in again. Okay, and now we see ZTS. Okay, we satisfied the S and the Z. We're good. But this is the same length as this. Either could be the answer. So we just move left inward again because these are both the minimum length. So we move L in. And now we're right back to square one. We're missing a Z and we need to move right forward. So let's move right forward. We need to satisfy now. And the only way we make advanced progress towards that is by moving right forward. So now let's move the right forward. And now we see I'm out of characters that can put me into a position to satisfy the requirements. And therefore, my search is over. And that means my answer sits right there. That is the answer because what we did was at every single step, we made a decision. What is the best choice for me? If this window does not satisfy, I need to keep moving this way. If my window is already satisfactory, I want to minimize by moving my left inwards. As soon as the window stops satisfying my requirements, I'm back to expansion. And that's basically how this works. That's how the two-pointer approach works. There's a tiny tweak and optimization you can make, which is explained in the LeetCode solutions, but this is the basic approach to this problem. And why don't we do an analysis of how this improves what we saw before? So let's try that right now. Okay, so let's do what we did before with the same string. And let's see how many searches we do at any certain indice. So let's put my left and right. So what I'm going to do is I'm going to do work at this window position. So let's put a 1 there. And I see that this does not satisfy, so I move right forward. And then we would entail work at this positioning as well. So what we would do is put a 1 there. And then we see this window still does not satisfy, and we move forward. And again, we mark 1 as doing work at this window. And then we move right forward. And we see now we have a winning window. And we did work at this indice, so increment that to 1. Okay, so now our job is to retract the window. This was our best answer, but we'll try to bring left in. So let's bring left inwards. So what we're going to do is we're going to bring left in. So let's do that. So we brought left in, and this entails more work. So we're going to increment that. Okay, and then we'll try to bring left in again. And we're still satisfying, and let's increment the work done there right now. And then we're gonna bring left in again. And then that's going to entail more work and another check. So this is a rough amounting of the amount of times we're gonna do work at any certain indice. So this is much better than what we were doing before. What we were doing before is many, many touchings of a certain indice and doing a lot of work at each of these indices. But as we see, any indice at maximum can be touched once by the left pointer and once by the right pointer. So that's what this solution provides to us. It tells us that any element is never gonna be touched more than twice. So that is the key to the solution and what keeps it linear in time. So let's look at the time and space complexities for this. So it's a lot more straightforward to analyze the time and space when you see the code. And the code is in the description, you can look there, but we can actually conceptually just think about this. So the time complexity. As we saw, the traversal itself is going to be linear in time. Any single indice can only be touched at maximum 2 times if we go all the way down with the right pointer and come all the way to the right pointer. So what we see is that that entails a linear time. The amount of work we do is going to scale in a linear fashion as the input gets very large. With our first approach, what we're going to do is for every left boundary, we'll have even more right boundaries to do. And then that's why that's n squared work instead of this being linear in work. So what we also need to take into account is that hash table I had right here takes time to build. And it would take the length of t, the length of the character string t, to build that hash table, that requirements hash table. So it would become the traversal time plus the time it takes to build a hash table for the time complexity. And then the space complexity is going to be O of s plus t. Here's a worst case we need to consider. If every character in t is unique, we're going to have t hash table mappings. Every single character will be A mapped to 1, B mapped to 1, C mapped to 1. And they're just going to have a key for each of these characters. So in terms of when would we have S, but why is S in here as well? Well, as we're keeping our running window, as you'll see in the code, we need to keep how many characters are in the certain window we're considering. So if you see this example right here, we would need to do the whole string as our window. If the window is ever...
I think that sort of explains enough. And so there's one explanation of the two pointers. Why did I say 2 pointers in a hash table here? I was wrong. Merge intervals here. So Brendan Fredelis is another one. He's pretty cool as well. I actually had a few from him that I thought would be worth watching. So let's look at all of his videos. I wish this guy was doing more, had done more stuff, because his sliding window. So that was just 2-pointer. Let's watch his sliding window.
In this video, I'm going to explain the sliding window technique. This is a very powerful technique for improving the time complexity of your algorithms. And if you watch till the end of this video, you'll be able to use this technique in your coding interviews.
I love it. Like, he's got to be like 15 or 16 here, but he comes off as super smart. So I really love it. It's like
If you find these videos useful, please like, because it helps out a ton, and subscribe so you can see future videos in this series.
Yes.
With that, let's get into it. The easiest way to understand the sliding window technique is through an example. And in this example, we're going to find the maximum sum of any contiguous subarray of size k. So in this array, that means we want to see which group of 3 elements that are next to each other have the greatest sum. So here the options are 2, 3, 4, 3, 4, 1, or 4, 1, 5. Which of these has the greatest sum? One way we can solve this is through a brute force approach, where we iterate over every element in the array, and then we look at the k-1 elements to the right of it, calculate the sum, and then advance to the next element and do that again. So first, we're at element 2, and then we see, what is the sum? The sum is 2. Then we add 3, it's 5. Then when we add 4, it's 9. So at this point, we see, what's bigger, the max or the sum? Well, we start the max at minus infinity before anything. So now 9 is greater than the max, so we update the max. So at this point, we advance to here, and we see what are the sum of these 3 values. We see it's 3 plus 4 plus 1, that's 8. Is 8 greater than max? It's not. So we advance again. So we see what is the sum of 4 plus 1 plus 5? That's 10. Is 10 greater than the current max? It is. So we have 10 here, and we update the max. So now we're done because we can't go any farther, so we know the max is 10. We can solve this problem faster, though, because this algorithm takes O of n times k time, which is slow for large k. The reason for this is the outer for loop takes O of n to iterate over every element, and the inner for loop takes O of k to compute the sum for each group of k elements. And as you can see in this example, for k equals 3, we compute the sum here, we compute the sum here, and we compute the sum here. And this is a lot of overlap. And anytime we see overlap in our computation, that's a source of possible improvement, because we don't want to do a lot of repeated computation. So using the sliding window technique, we're going to solve it similarly, but we're going to try to remove some of the duplicate work. And we're going to do this by having a sliding window with 2 indices, one for the start of the sliding window and one for the end. And anything inside the sliding window will be part of our sum. So at the beginning, it starts and ends at index 0, so the only element in the sum is 2. And as long as this sliding window is smaller than k, we're going to increase the size. And we'll increase the size by incrementing the end of the sliding window. So we increase it, and now the size goes from 1 to 2. And at this point, we see 3 has entered the sliding window, so we're going to update the sum. And again, the sliding window is 2, and we can go up to 3, so we're going to increase the size again. So now 4 is entered, so the sum is 9. And at this point, the size is 3, so we want to check, is this sum greater than the current max? Well, the max is minus infinity, so we're going to update the max to 9. And now, since the size is 3, we can't make it bigger anymore, but we still want to advance. So we're going to advance by increasing the ending pointer and also increasing the starting pointer so that we move forward in the array without increasing the size. So we increase the end, and now 1 enters the sliding window, so the sum becomes 10. And then we increase the start, and then the 2 leaves the sliding window, so we subtract 2. And again, now that the size is 3 again, we check, is 8 greater than the max? It's not, so we continue. We increase the right, so we add 5, so it becomes 13. Then we increase the start, and we subtract 3, so this becomes 10. So now we see, is 10 greater than 9? It is, so we update the max. And now that we can't iterate anymore, we see the max is 10, and we return that as the final answer. And this is faster than the previous approach because we're avoiding a lot of duplicate work. We're moving the sliding window over one at a time, and we're keeping a cumulative sum where we add to the sum and subtract from it. We don't have to recalculate the sum for every k elements, and this takes O of n time.
Now we're ready to implement the algorithm.
So let's go back to the grokking just at this point. So that's sort of, what do we have? We've got sliding window. We have 2 pointers, which is a variation on the sliding window. But I mean, so it's just sort of like, this is another way that we can go about getting ourselves ready to jump in on the coding interviews and so on. So let's go back to watch a
First,
solution.
we're going to define our max sum variable, which will get initialized to minus infinity. So max sum equals float of minus infinity. Then we're going to define our start pointer, which will be the beginning of the sliding window, which we pointed to 0. And we also want to keep track of our current sum, which will be the sum of all the values inside the sliding window, which will start at 0. And the ending part of the sliding window will be the variable end in this for loop. So for end val in enumerate array, we're going to update our current sum to account for this new value. So current sum plus equals val. And then if end minus start plus 1, so this is the size of the sliding window. If this value is equal to k, that means we want to check, is the sum inside the sliding window greater than the current max? So then we'll say max sum equals the max of the max sum and the current sum. So at this point, the max sum has been updated, and we want to advance the sliding window without increasing the sliding window greater than k. So we're going to subtract the start value from the sliding window, so current sum minus equals array of start. Then we're going to advance the start pointer, so start plus equals 1. So on the next iteration, the end pointer advances, but because we move the start pointer forward, it's still going to be size k. And then once we exit this for loop, we'll be done, so we simply return max sum. So I have a test case that we can run, and the answer in this case will be 10 because of the subarray 415 sums to 10. And here we can see the output is as expected. Now we can move on to a more challenging sliding window problem. In this problem, we're given an array of positive numbers, and we want to find the size of the smallest contiguous subarray whose sum is greater than or equal to s. So in this example, s is 7, and the answer is size 2, because the contiguous subarray 2, 5 has a sum greater than or equal to s, and the size of this subarray is 2. We're going to solve this using a sliding window technique, but different than the previous problem, this sliding window has a dynamic size, where in the previous one had a fixed size of k. So we're going to start by placing the first element into the sum, because this element of 2 is inside the sliding window. Now we're going to check, is this value greater than or equal to s? If it's greater than or equal to s, then we're going to want to check, is this size less than the current min? And we're also going to want to try to decrease the size of the sliding window. But because this value is less than s, we're going to continue expanding by increasing the sliding window. So we're going to increment the end pointer of the sliding window, and we're going to add 4 to the sum. So now we have 6, and 6 is still less than 7, so we're going to continue to expand the sliding window. So we expand again, we add 2, so it's 8. So at this point, 8 is greater than or equal to s. So this contiguous subarray is a possible answer. So we want to check, is this size of 3 less than the current min size of infinity? It is, so we're going to update the min size. And now we want to see how small can we make this contiguous subarray, because right now it's at size 3, but we want to see if we can make it even smaller. So we're going to increase the start pointer and subtract this 2 from the sum. So now we have 6. But here we see this is no longer valid because it's size 6, or sum is 6. So we're going to continue expanding. So we're going to expand by increasing the right pointer. So we add a 5. So now we have 11. And here we have
a value greater than or equal to 7. So we're going to check, is this size of 3 less than the current min? It's not, so we're going to continue. And now we want to see how small can we make this sliding window. So we're going to increase the start pointer. So we subtract 4 from 11, so we have 7. And now we see this is size 2. Is this value less than the min size? It is, so we're going to update the min size. So we update it to 2. And now we want to see, can we make this sliding window smaller? We can, so we make start, go up 1. And now the sum becomes 5. And because 5 is less than 7, we want to start expanding again. So we expand, and we add 1, so it becomes 6. And 6 is still less than 7, so we're going to expand again. We expand, and now it's beyond the bounds of the array, so we're done.
First we'll set the min size, which we'll set to infinity, because we haven't seen any subarrays yet. Then we'll set the start of the sliding window to 0, and we'll maintain a cur_sum, which will start at 0. And like the previous problem, this will have the sum of all the values inside the sliding window. And we're going to iterate over all the elements in the array for end val in enumerate array, where end is the end of the sliding window and val is the corresponding value. We'll first update cur_sum, which will have val added to it as we expand the sliding window. If cur_sum has a value greater than or equal to s, that means we want to check what is the size of the sliding window. And if this sliding window is smaller than the current min, then we want to update the min. And we also want to see how small can we make this sliding window. So we're going to say while cur_sum is greater than or equal to s, we're going to check for these things. So we'll have min size is equal to min of min size and end minus start plus 1. And n minus start plus 1 is the size of the current sliding window. And then after we do this, we want to see, can we start to make the sliding window smaller? So we're going to subtract the start from the sliding window. So we'll have cur_sum minus equals array of start. And then we'll move the start inwards. So when we move it inwards, we're decreasing the size of the sliding window. So then once we go back to the top of the while loop, it'll check again. Now that we have a smaller sliding window, is this condition still true? If it's still true, we'll see if we can update the min again, and then we'll try to make it smaller again, and so on. And then after we do this, and after we iterate over all the values in the array, we simply return the min size. And now we can look at this example case. So we have this example of 2, 4, 2, 5, 1 with s equals 7. And in this case, the answer is 2 because the contiguous subarray 2, 5 is the smallest contiguous subarray with a value greater than or equal to 7. And the size of the subarray is 2. So we can run this. And the output is as expected.
Thank you so much for watching. If you like this video, please like and subscribe. And if you stayed till the end, comment down below saying you stayed till the end. I also offer tutoring on computer science courses and interview prep. So if you're interested, you can sign up in the description down below. Thanks again, and I'll see you in the next one.
There we go. So, hey, why is that muted? Okay. So that was two of the major pattern. Two of the super early patterns. Just to give you a sense of what you are going to get into. This is really interesting. I hadn't noticed this one before, but that's really valuable to see. And then I'm going to skip this one for now. I will open it. It's one more solve. She's doing the same sort of thing where they illustrate the algorithm with visual examples and then solve it. And I think it's still really useful to compare the just to get it within the major pattern and then go back to your LEET code and try and solve one. But I also wanted to draw attention before moving forward to the educative site again, grokking the behavioral interview, but this one is completely free. So you get the entire course all together, and you can see what they're on about. So this site, Educative, you can look at their courses. They had a filter. How did I find this last time? These are in progress courses. Oh, that's my courses. I want explore free. So if any of these are of interest to you, I actually kind of want to learn Rust. So I think that one would be interesting. What's this? Java, C++, functional programming. What was... Oh, here's one on Flexbox. 2, 3, 4 trees. I don't know what that is. I'm going to read that later. Garbage collection. So anyways, those are a bunch of free courses that you can get. I think the behavioral interview one is going to be useful for you. But we'll look at that again in a few more weeks after I've had a bit more time to dig through it and go into it. So here we go. Merge intervals. Here, where is she? Here she is. Merge intervals.
Hello and welcome. Today we'll be doing a question from LeetCode called non-overlapping intervals. It is a medium. Let's get started. Given a collection of intervals, find the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. Example 1, given the input 1, 2, 2, 3, 3, 4, 1, 3, we output 1 because 1, 3 is the only interval that needs to be removed to make the others non-overlapping. Here, 1, 2, and 2, 3 share a boundary, but that's okay because they're not overlapping. Example 2, given 1, 2, 1, 2, 1, 2, we output 2. We need to remove 2 of the 1, 2s because they're all the same interval to get that single 1, 2 that's not overlapping. And given the input 1, 2, 2, 3, we output 0 since 1, 2, 2, 3 don't overlap. Now, this question is asking to find the minimum number of intervals we need to remove to make the rest of the intervals non-overlapping. But this is also equivalent to finding the maximum number of non-overlapping intervals. If we had the maximum there, we would automatically remove the minimum. So how do we find the most number of non-overlapping intervals from a given list of intervals? Well, what if we sorted them by start time and we removed every interval that overlapped with the earliest interval? Then we find the next earliest start time and remove anything that overlaps with that and continue through. Would this give us our answer? Would this approach give us the most number of non-overlapping intervals? While this is a good intuitive guess, this actually would not work. For example, if we had this example right here, suppose this is a number line, and on this number line we have interval 1, 8, 2, 3, 4, 5, 6, 7. If we were to pick the earliest starting interval, we would have picked this top one right here and removed all the others and only be left with one interval. But we wanted the maximum non-overlapping, and clearly the answer should have been 3, so that wouldn't work. Now, what if we take a different approach and try to find intervals that have the shortest interval? So the smallest difference between start time and end time, that way we can fit in more if we only take the smallest intervals. And, of course, go ahead and remove the ones that overlap with the shortest, then take the next shortest, remove all overlaps from there. As you can see, this wouldn't work. If we had done that, we only would have been left with this interval right here because we would have removed both of these, and that was not what we wanted. What if we picked intervals with the least amount of conflicts? So if we do that, then that means that we have to remove the least number of intervals. This answer is a little bit more nuanced, but this again fails to work, as seen in this example right here. This interval overlaps with 3 others, this one, and this one, and this one, and all 3 of these have 4 overlaps themselves. two of those and these two right here. This one has only 2 overlaps, and the same scenario for this as on this side. It's just a mirror. And if we go with this approach, we would end up picking this interval first, removing this interval and this interval due to overlap, and only be allowed to pick one on each side, either this one or one of these 3, ending up with only 3 intervals total. But we know that we should have picked the top 4 right here. So again, this approach does not work, but what does work is if we finish our resource the fastest to take the next interval. So what this means is if we actually see intervals that have the earliest finishing time. So instead of sorting by start time, we sort by finishing time and take the earliest finished interval, remove all the overlapping ones, then take the second interval that finishes the earliest. This way we're freeing up our resource to make sure we can take as many intervals as possible. And this actually works, because if we look over here, the earliest finishing one would be this, and this, and this, giving us our maximum number of non-overlapping intervals, 3, and that means we only need to remove 1 interval. Same case here. We take this, and we take this, because this finishes first, remove all the overlapping ones, so we would have removed this, and the next earliest finishing time would have been this interval. And similarly, we would have picked this since it finishes the first, remove all overlaps, remove these 3, take the earliest finishing time again, remove overlaps, earliest finish time, remove overlaps, earliest finish time. So this is the approach that we will be taking. Let's just go ahead and code this up. If you've ever taken an algorithms course, you know that this is your typical interval scheduling problem, and you can actually use previous days ahead, induction to prove why using finishing times would actually give you the right answer. But I'm just going to go ahead and code this up. So first, if intervals is empty, I'm going to return 0 since there is nothing for me to remove. If not, I'm going to go ahead and sort by finishing time. So intervals.sort. And the default sort would be to use that first value, but we want to use finishing time. So here I'm going to use key equals lambda x, where x is whatever's indexed at position 1. That's
Oh yeah, no, these ones are like really hard, and that's why recognizing the patterns that come out will help. And so yeah, it's like this stuff. And the only way that you get this, because if you came into an interview for the first time, having never seen this before, you would be like, but if you had studied 5 other overlapping interval problems, and sometimes it'll be show me the non-overlapping one, and sometimes it'll be show me the ones that do overlap and or combine the intervals so that anyways, so the trick of doing the different puzzle types is to recognize them so that no matter which one shows up in the interview you're at, you're able to get it.
Second number. Now that we have our interval sorted by finishing time, I'm going to initialize remove to 0. So this is how many intervals we want to remove. And I'm going to have my initial end being intervals 0, 1. So this is my earliest finishing time. Now that I have that, I'm going to make a for loop 4 times in intervals. Start time is times of 0. And if this start is less than end, I'm going to increase remove by 1. And why am I doing this? Well, if I have a finishing time, and whatever interval I'm on right now, that start time is less than that finishing time, I know that there's an overlap and I want to remove that current interval. If that is not the case, all I'm going to do is update start, because update end, because that would be my new earliest finishing time. So else end equals times of 1. And once this is done, all I'm going to do is return remove. This almost works. There is one slight problem here. If I initialize end to that first interval's end time, we're going to have that first interval's start time be less than end time, and we're going to have an extra remove. So I just need a time that's less than that first end time. So I'm going to make it equal to actually that start time. So it never goes into this if case and updates end time for the rest of the intervals. This should now work. I'm going to run code. It's accepted and submit. And it works. Now talking a little bit about space complexity, time complexity, this is O of n log n time because we are sorting, and then we do another O of n iteration, but overall this is O of n log n time-wise, and space-wise we're just using end, remove, start, so that is constant space O of 1. As always, if you have any questions, let me know, hit up the comments below. Otherwise, I'll see you next time.
She was really good though, right? That was, she was really great. So those were 3 of the major patterns. I think if I was to do this whole course again, I would, now that I've found this resource, I would probably start by just doing 1 pattern a week. But yeah, the solution is super short for how hard it is to like wrap your head around, which also makes it the ideal kind of interview question, right? Because they want something that if you know what you're doing, you can solve it in a handful of lines of code. But if you don't, you can sort of not ever solve it or like really do something crazy and wild. But that also goes back to a criticism of the coding interview process, just because like, you know, they're really just testing to see if you have seen that exact problem before, not testing to see if you know what you're doing in terms of code. So where are we now? So what do we like best? 2 pointers, intervals, or what was the other one? 2 pointers and then, or sliding window. Sliding window, minimum size subarray sum, fruit into baskets. Do we feel up for let's do 2 pointers. Here we go. We have 2 sum. I did 2 sum the other day, so this one is squares of a sorted array, backspace, string compare, find the duplicate number, threesome. Threesome is really hard. You've done twosome? Here we go. Let's go to threesome. Oh, this is threesome discussion. Description. Here we go. Threesome. How do I do my share link again? Invite link. Send it to anyone you trust. Here you go. Everyone. I trust everyone on the entire internet. Oh well. That's okay. That's okay. We can actually, we don't have to live code it here. We can set out our timer. . And okay, C sharp. Okay, joshhaber.js. Let's see. We had Trish in the Pebs in the hot seat last week. So Pebs doesn't have to do the connection again. Edit timer. 30. How much time do we have left? 15. So let's call this one a 40-minute problem. Or let's do 35. 35 and save. And then accept read write. Guest user is anonymous, has read write access, and I assume you want JavaScript. Yeah, I mean, it's got to be. I mean, if you type, you should be able to. You should be able to live edit the thing here. Oh. Is it not working? Let me see. Save this file. Stuck at loading file tree. Oh, try now that I added the dot. Okay, you can move. Guest user left. Okay. Is that one? That one's Josh? Here, do you want JavaScript? Okay. We start. In theory. Oh, that is that must be Pebs then. Here we go. So maybe yeah, let me split these. In theory, you can access different files. I'm not sure. Somebody typed woohoo. Okay, that's fine. It's not JavaScript anymore. That's C#, the way it should be. We'll close the Josh one. There we go. And I'll bring one up too. Competitive, team-friendly programming with a timer. Okay, let me get this down to a... I typically can't actually do these in a half hour, which is why I need to practice so much as well. But, okay. Given an integer array of nums, return all of the triplets such that I does not equal j and does not equal k. And j, so where all of the numbers are unique, return so. Well, wait a second. That doesn't make sense. Oh. And the value is... So how does this make sense to me? Return all of the triplets. 1, 2, 3. Such that I is not equal to j. I is not equal to k. J is not equal to k. So how does this work? Because that number is the same twice. Oh, the index, where 3 different numbers were the index. Okay. Okay. And do they have to be contiguous? 1. No. They don't have to be contiguous. Oh, sorry. The question is threesome. And Josh, do you have that one as well? There we go. So, and this one is medium, and it came from, if we look at the Sean, let's go GitHub interview prep. I'm going to find the patterns. This one fell under the 2 pointers pattern. So in theory, if you're seeing this, you should have 2 pointers. But is it 3 pointers? Let's try with 3 pointers. Maybe. Int for I is less than nums dot I plus plus. Okay, but it is nums dot length minus 2. Then, Oh my God, I'm having so much trouble figuring this out in my head. For j equals 1, j, this doesn't make sense. Okay, we know we have to visit each element in the array at least once, right? So it's less than nums. Okay. So j equals 1 and int k equals 2. Okay, then we say if nums dot length is less than 3, return okay, so if I run this, cannot generic list yeah. It's I also started by writing 3 loops and I'm like, what the shit is this? This is stupid. Don't do it. I don't think you can actually get away with this one without doing 3 loops, but it's and it's only medium hard. Is assigned a value, but it's never used. I'm fine with those. Those are warnings. But this one cannot implicitly. Oh. This is strange. I don't know. Can I do that? Well, how do you return an iList? Okay, let me try this again. Nums less than 3. So new list int with nothing in it. Why? Oh shoot, I did not mean to actually submit. Cannot implicitly convert type. Wait, so what do? Do you do this? Okay. I don't even know what's going on with that. So how do I return? So what is this saying? Just do this. Return new list. Well, okay. I'm going to try that. Type, that's supposed to be an int. Well, okay, so it's the wrong answer, but at least it's fine. But what if I do a new iList int? Okay, I'm just still trying this out to see what I can do. Okay, let's run this one. Comma expected. Yes, you're right. Comma is expected. New expression requires, yes, right there. Run that one. Okay, good. See, I did it. Here we go. So if nums dot length is less than 3, return new list int iList int. Okay, that's step 1. Now let's create a var valid equals what does valid equal? Is equal to a new list of list int with nothing in it. Now Well, actually, oops. So I do this, return valid, semicolon. Now, int I for I equals 0 less than nums dot length okay I plus plus, and then that is nums dot length minus 2, because that is the length of the threesome. Int j equals 1, int k equals 2. What else could we try? So we have to try every single combination of 3 values. So let's start with this. If nums at I plus nums at j plus nums at k equals 0, then valid dot add new list nums I j k. How's everybody else doing? Anybody? Okay. So, and then at the end of going through that, yeah, okay, good, because this is killing me as well. I'm going to return valid. So, is there a situation where I can do this? So let's say, let's update my test case to say just the first one. It's actually no iteration at all. But this should return 0, 1, 0. So let's run the code. This should give me using the generic type list T requires one type arguments in solution. Ah, dummy. New list int. Okay. I'm struggling with the language more than I should, more than I normally do. Okay, so this works in this case. Now, what else do I need to do? I've got to make sure that I increment J and K. For J equals I plus 1 to J is less than nums length minus 1, J plus plus, so that's all well and good. Give me this test case back. Actually, let's run this one. Right. Okay, so let's go back to the array that has threesome in it. Wrong answer, but what did I return? I returned well, that's really strange. I actually returned something. This one's correct and this one's correct, but my IJKs are not the same. So, for K is equal to J plus 1. This might be the brute force approach here. K is equal to J plus 1. K is less than nums dot length. K plus plus. So, if we are looking at a case where I, J, and K will never be the same, the only problem is that it probably tests a couple of conditions more times than they should go. So I output the response. What if I store my potential responses in a dictionary? So let's say this. We will say dictionary I'm just going to go string list int equals new string list int. Copy string list int. Okay, so I, j, and k, each of these can be declared in place. Int, int, int. Now, instead of adding to valid, I'm going to say string I'm going to say, and this is actually going to be a hash set. No, this is going to be a hash set string new hash set string. I'm going to say we have found a valid one, so the the hash set needs a name. Found. I'm going to say this has been found, so we are going to say found dot add this new keyboard, this fancy new keyboard, this Corsair K57 has the most unfriendly N key. I'm always missing my N. So I'm going to make a string dollar I J K, but I'm also going to sort the, so I guess I have to say why don't I say hash set No, I'm just going to do a string because I only have 5 minutes left, even though there is a probably better way to do this. Can I actually sort a string? Sort a string, C#. Is there a simple way that I can sort the characters in a string alphabetically? String order by okay, so oh no, where's my problem? Here it is. Okay, we're gonna do new new list string 3 minutes. Okay, 3 minutes. Do we need an extension? New list character I, comma, j comma k semicolon found. We are going to add okay, we're going to call this var key is equal to new list car ijk. Say if key string dot join dot order. What is it? What is the order? What was it? Order by CC. Okay. Okay, if string dot join yeah, okay, so let's what was that original one? It was string.concat dollar dot order by c.c. Okay, so that should give me the key. If the found does not contains, if not found dot contains key, and we are first going to say found add key, and we are also going to say, oh my god, 30 seconds. Okay, run, and then I return valid. So I add it. Oh, so many broken codes. So many broken codes. Okay. Invalid expression term int on int 1. Oh, int k equals. Run the code again. Wait, how do I stop the damn timer? Okay, there it is. Okay, I got the wrong answer, but I really feel like I was on the right track here. I feel like I was about to get that one day if I just kept trying. So, let me see. How long do we have? This is, okay, I kind of want to solve it myself, but this is the point where we have to go to the discussion and we have to look for easy explanation without a set. Okay. Python 3, 10 lines. Let's look at some of these explanations and see. So, how pretty much the only difference here is that we create a set which stores a tuple of the triplets that sums to 0. I'm having trouble reading this though, so let me see. So the set, sorted numbers. You sort your numbers. Okay, for I, I'm not getting where K is. Yeah, I know. That's the problem of the game. Okay, here's what I'm going to look for: a C# one or maybe a JavaScript one. Those are easier. So let me look for a C# here under discussion. Here's a C# solution. How did you do, Pebs? Are you still trucking? 15 lines, O of n squared. Here's 2 pointers. Here's a whole bunch of different solutions. Yeah. Okay. So we all got trying to do it without a loop. Oh my gosh. So what was this? This one counts as a medium, so we don't have to be too shy about our result here. So here, first one they're doing is they are sorting their list. That is something that I did not do. So your n is nums.length. Okay. Your results, you have your results. Now, we say for every number in the array, if I is greater than 0 and the number and the nums equals nums at I. Right, trying just to use pointers. I see. Var left and right. Oh, so are they... While the left is less than the right, so are they starting... But I starts at 0, and it goes through every number in the array. Nums left at num right. Sum. If the sum is 0, we add the result. Well, left is... Okay, so the left plus 2, the right minus 2. Well, I feel like that one needs comments to explain it. Sort, pick the second. Okay, well, you've got a lot more of what people seem to be using in their algorithms. Sort, pick the second, hash, find next, and skip. That's not clear. Okay, this one, basic idea is that after given array is sorted, after the array is sorted, start from the end of the array and calculate the number needed to satisfy a plus b plus c equals 0. Given we get a number from the array, then b plus c is equal to 0 minus a. Then we search the rest of the array. We get number b, get c. Then it's just a binary search rest of the array for c. If it exists, we get a triplet. to make sure triplet does not duplicate, just keep track of A and B. Make sure it is not the same as previous, because the array is sorted, the same element is always next to each other. So, yes, so that's what you start with. Sort the array so the search is quicker. Okay, so they're sorting the array so that you can exit early if you break the, if you break well above 0 or something. Okay. And so you start at the last element of the array. So you start at the largest element, and then you work in towards the front using... Oh, so you start at the end, or you start at one end, you pick the number at the other end, and then you run your loop across. And then you move your pointer in, and then you run your loop across. And you move your pointer in, you run your loop across. Does that sound like what's going on? If I does not equal, okay. Right, so if not at the start of the loop and previous number equals the current number, no need to continue. The triplet, if there is one, will be the same. Right, okay. Calculate how many we still need to compose the triplet. Update the previous number. How did we do? Did anybody get it? Well, there's a reason we practice these things. Not yet. Well, okay. And here I am already looking at solutions. But this is the way they say you're supposed to do it. They say that you're supposed to, if you can't solve it within the time available to you in an interview, you're better off. So they say you're better off looking at the responses and then, because there's 1,800, there are 2,000 problems on this website. So you can... Dealing with time. Yes. Yeah. That's actually, that's one of the best ways that LeetCode, for example, has to teach you, why you have to deal with your O of N, because they start presenting you with these test cases that are like megabytes and megabytes. And so that's part of the fun. So, well, I'm going to submit this one the way it is now, even though I know it's wrong. Because if you submit, it actually saves your code in the state that it's in. So now I can go back to running this test case. I just want to see if I'm actually getting my keys. Right, so 0, 1, 1, that doesn't make sense. And 0, 3, 3, that's impossible. 1, 2, 2, that's impossible. So but what isn't is we go back to you actually only need to nums dot length divided by 2. for int j is equal to nums j is equal to nums dot length j no, let's do every number in the array, one loop, and no. Right. Do you have one? Here, do you have a... You can't log in and share your code. But you can do a paste bin or something. Pastebin.com? Yeah. So you can just paste something into Pastebin and share it there. Oh, see, that's supposed to say me. Strange. Anyways. It's not supposed to be restream. And then right, so sorting, they sort the numbers. We'll wait for Josh's answer. Let's look at this one. Right. So if I is greater than 0. Okay, and this is JavaScript. Okay. How do I copy this? Here we go. Let's run it. Copy. Copy, 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 copy. And we'll go over here for C# onto JavaScript. Paste it in. Start this. We're going to run Josh's code. There it is. And there you go. And then it says, now try foursome. Okay. So let's see. You got 30% and whatever. Just being done. Oh my gosh. Look at this. This is insanity. Like, they're... Oh, did you? Okay. Well, I think that's part of passing the interview is having done these things ahead of time. So it's like, it's not really cheating. It's not really cheating so much as like practice and education. Anyways, that was awesome. That was fun too, I think. It was fun even though, I stubbornly want to figure out how to solve it in the way that I was doing it. That was clearly going to end up being wrong because everybody else has done it. So what are we doing here? So you start if the length is not greater than 2, you can't have a threesome, so you just send it back. So you start with a hash, you create a triplet, you sort your array, and then for each number in the array, if the nums at 1 is greater than 0, break. What does that? Why is that there? If nums at I are greater than 0, break. Then you start at I plus 1, you end Oh, okay. So you can eliminate half, like, right. Okay. Right. Okay. Because it's sorted and the goal, let me see the description again. The description is where the numbers all add up to 0. So if it's greater than 0, yeah. Let the start equal I plus 1. So for each number, you start at that one, and then you end at the final one. And then while the start is greater than the end, to get everything, you go doop, 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 right? But you decrement by 2, and you go, oh no, that's decrementing by 1. Oh my God, I'm stupid. Right, so you're here, and then you go, and then you move forward 1, and you go, and then you move forward 1, and you go, and if you find a matching triplet, and the hash checks if the value has been matched before. Right. Because, let me see. So the total is equal to the current number plus the start and the finish. If the hash, right, and that's what I was trying to do with my hash as well. If the hash has not been added yet, you add it to the hash, and then you add another triplet, and then you change otherwise, return, otherwise, return. Okay. That's it. I understand it. Because it's sorted, duplicates will always be in the same order. Right. So, and that doesn't matter. So, there we go. That's the week. We're a little over time, but that was super fun. And like a little brain melting, but that's part of the way to get better at this stuff. Next week is the actual real life start of system design interviews, and that's the story. So if you are back, we will see you again. I know Rajat's going to be watching over the weekend, and thanks for coming along and playing Melt My Brain. Here we go. Oh, good. I'm glad. I think this is fun where we do the coding stuff, even though it's hard. Close all tabs, close this. And all right, stopping the stream.